Hello, my name is Dario Gavrila. For the past 4 years I have been heading the Intelligent Vehicles Group at TU Delft in the Netherlands. Before, I worked nearly 20 years on driver assistance at Daimler R&D in Germany. It is a pleasure to talk about what I believe is a big remaining challenge for intelligent and self-driving vehicles, dealing with an urban environment and in particular interacting with vulnerable road users such as pedestrians, cyclists and other riders. These road users are not always easy to detect, and figuring out their future motion is even harder, as they are highly maneuverable. This video shows the output of a state-of-the-art object detection method, faster RCNN. Detected pedestrians are shown in green and riders are shown in red. Results are quite remarkable, considering that these are single-frame results before any tracking. Even persons which are partially occluded are well detected. This video showed what is possible when training state-of-the-art object detection methods on a large dataset. In this case, we used the EuroCity person dataset, which we recorded in collaboration with Daimler. It involves nearly 250,000 of distinct persons annotated, coverage from 31 cities across 12 European countries, diverse weather, 4 seasons, day and night, and accurate manual annotations. By its size, diversity, and annotation accuracy, EuroCity persons bring person detection benchmarking to a new level. We also implemented an evaluation server so that authors can submit their results and compare themselves to the state of the art. As seen in the previous video clip, we're meanwhile doing quite well in detecting the vulnerable road users at a particular time instant. I believe this holds for the vehicles as well when considering the state of the art. What is still a big challenge, though, is predicting how a traffic situation will evolve. For self-driving vehicles, anticipation is the key to a driving style that implements a good trade-off between comfort and time efficiency. That means smooth accelerations and decelerations, no jerky movements on one hand, and still getting ahead on the other hand. Desired is an adaptive driving style that involves slowing down when potential danger lurks and speeding up if the coast is clear. The attentive human driver is very good at this, based on his understanding of context, and this aspect is still lacking in self-driving vehicles. Addressing this is a main focus of our research group at TU Delft. We are interested in motion models that predict the future well. What does this mean? Granted, uncertainty is a fact of life. See the top image. If one expands the prediction horizon, the potential region where the pedestrian will be expands. But let us look at a given prediction horizon, say 2 seconds ahead. The left bottom image shows a prediction of a motion model, which surely will be correct, but is not very specific and thus not very useful. In the middle bottom image, we have a model which is very specific, but it's likely to be incorrect. The model in the right bottom image seems best, as it represents the uncertainty more appropriately, in the sense that it accounts for both the cases that pedestrian might continue walking or might stop at the curbside. So how do we evaluate the predictive motion models? In an offline setting, we know the future object position, so we seek motion models that maximize the likelihood of the future object position under the predictive distribution. Let's now turn to what visual cues these motion models would use. Early on in 2013, we first considered motion models that would use only positional cues regarding the object of interest. We see 3 dots representing the positions of 3 pedestrians when viewed from the driver perspective. The horizontal line denotes the horizon. Time for a little quiz. Which of these pedestrians will cross? Well, the pedestrian dot on the left seems to be moving leftwards, and he seems to be on the safe side. But the 2 pedestrians on the right are wobbling laterally, might be about to come into the vehicle path. Using this point target representation, it's hard to figure out what is going to happen. And indeed, in our experiments, we found that we could detect crossing behavior only after it already started using the point target cues. It is worth mentioning that most pre-crash systems on the market still use only these point target cues in their motion model, so it is no wonder that these systems tend to react rather late to avoid false positives and thus have a reduced benefit. In later work, we investigated whether image features like optical flow could improve prediction performance. In this video clip, the direction of optical flow within the object bounding box is color-coded. Looking at it, it's still hard for a human observer to understand what is going on, but there is a certain promise that this enriched object representation could be useful for a pattern recognition algorithm. It might, for example, detect slight local changes in dynamics, such as decelerations or accelerations at the feet region of the pedestrian. We developed an approach that represents the image motion of the walking person in a latent space using Gaussian process dynamical models. Each pedestrian pose, denoted by a red bounding rectangle in the left window, is represented by a point in 3D latent space in the right window. Walking motion in image space is mapped onto a toroidal structure in latent space. Motion modeling and prediction happens in this latent space. The pedestrian icon that appears on the lower left indicates what the system believes the pedestrian will do at the curbside: continue walking or stopping. Using this approach, we were able to predict pedestrian crossing 200 milliseconds earlier than when just using the point representation. This is valuable extra time to perform emergency maneuvers like braking or steering if needed. Let us now look at the actual view that a driver would have of the traffic situation, which I showed earlier in a reduced form. Quiz time again. Which of the three pedestrians will likely cross? Well, it is clear that the blue pedestrian on the left will not cross. Most people would argue that the brown pedestrian on the far right will likely stop. Why? Well, for one, he has seen the oncoming vehicle. If one looks carefully, one even observes a slight deceleration when the brown pedestrian is near the curbside. How about the green pedestrian further away? Most people would claim he will cross. In this video, this turned out to be true, but I would argue that based on the information seen so far, this is pretty much anyone's guess. The green pedestrian is still too far from the curbside to allow us to infer anything useful about crossing or stopping. We developed the dynamic Bayesian network to model these relevant context cues. The model incorporates whether the pedestrian has seen the oncoming vehicle, whether the pedestrian is near the curbside, where a dynamic change might happen, and whether the oncoming vehicle and the pedestrian are on an immediate collision course. Otherwise, the pedestrian will not be affected in his behavior and always cross. More specifically, the dynamic Bayesian network considers a set of primitive motion models for the pedestrian, in our case constant velocity or constant position. A latent switching state, shown in the DBN diagram by a blue rectangle, determines which of the basic motion models is active at the current time instant. The clue of this approach is that we will have the switching state be conditionally dependent on the latent variables that represent the previously mentioned context cues. See the red rectangles. These latent variables are being informed by measurements. For example, we can measure the pedestrian head orientation versus the vehicle and use this to inform the sees vehicle latent variable. In this video clip, predicted pedestrian position by the DBN is represented by a blue elliptical region on the ground plane. You can see how this elliptical region suddenly shifts back to the curbside for the brown pedestrian on the right, after this pedestrian has seen the vehicle. For the green pedestrian further in the back, the DBN model, however, predicts crossing behavior. It should be emphasized that there is no hard-coded rule in this model that would, for example, say if the pedestrian has seen the vehicle, then he will stop. The switching state depends probabilistically upon the context variables. Which context variables are relevant is our expert knowledge that we have handcrafted into the DBN representation. Yet, how this dependency is quantified is learned from training data by observing many actual crossing and stopping behaviors. It is instructive to inspect the inner workings of the DBN during inference. Let's consider the scenario where a pedestrian walks towards the curbside, at some point looks towards the oncoming vehicle, and then stops. On the right, we see a diagram with the current estimates of the latent variables as time progresses from left to right. We will be examining two snapshots A and B of this sequence shortly before and after the pedestrian has noted the oncoming vehicle. This as shown in the two images, which correspond to the two vertical green lines in the latent variable diagram on the right. Looking at this latent variable diagram, we see that during the sequence, the @curb variable, initially false, becomes true as the pedestrian reaches the curbside. Also, the sees vehicle and the has seen vehicle variables become true as the pedestrian turns his head toward the oncoming vehicle. The on collision course variable becomes true as well early in the sequence. As a result, the switching state representing which basic motion model of the pedestrian is active changes from walking to stopping. In snapshot A, the pedestrian is still far away from the curbside and has not seen the vehicle. The graph below shows the predicted lateral position with increasing prediction horizon for various models at this particular time, A. We have the LDS, the linear dynamical system, which is in essence a Kalman filter. We have the switching LDS, multiple motion model with switching state but without context, and we have our full model, the DBN shown in previous slide. We see all models output a straight line, predicting that a pedestrian will continue walking, which makes sense. There is no evidence to the contrary. In snapshot B, the pedestrian has neared the curbside and has started to look at the oncoming vehicle. In the graph below, the models that do not use context, like the LDS and the SLDS, still output a straight line predicting the pedestrian will continue crossing, which is incorrect. The full context-based model correctly estimates that the pedestrian has seen the oncoming vehicle and outputs a curve which bends towards a vertical line, in essence correctly predicting the pedestrian will stop. We now turn to a quantitative evaluation. We use the log likelihood of the actual ground truth position under the predictive distribution, 1 second ahead. In this table of results, the rows represent average results over several runs of a particular scenario. For example, whether on collision course, whether the pedestrian has seen the vehicle, and what his action was. The columns represent the various models tested from the rudimentary single motion LDS, the Kalman filter, to the more advanced multiple motion SLDS, and finally to the proposed context-based SLDS, the full DBN model proposed. The last column, PHDM, is a state-of-the-art method which does not use context and does not involve a DBN. It involves partial trajectory matching and is of a higher order Markov model. Looking at the numbers under the red rectangles, we see that the LDS perform poorly. High numbers are better. Looking at the numbers in the cyan rectangle, we see that there's little difference between the SLDS and our proposed model. This is not surprising since these scenarios do not involve a change in dynamics. On the fourth scenario, the fourth row, there is a change in dynamics from walking to stopping, and here our context-based model can shine versus a model not using context. See numbers in the green rectangle. We also see that the full model in the third column outperforms the PHDM method in the last column, the purple rectangle, across all scenarios. We extended the DBN approach to model the joint motion of a pedestrian and vehicle for the pedestrian crossing scenario. This in case that our intelligent vehicle only offers driver assistance and we would like to predict where the own vehicle is likely to go, being controlled by the driver. Both pedestrian and vehicle motion are now modeled by an individual DBN. The pedestrian DBN, shown in shaded blue, is the same as discussed before. The vehicle DBN, shown in shaded green, now contains a context variable which captures whether the driver has seen the pedestrian. The driver gaze direction is used as associated measurement. The two individual DBNs are linked together by means of a shared latent variable which captures whether the two road users are on collision course. This shared variable is shown by an orange rectangle in the diagram. In the video, we first see a scenario repeated where the driver is not looking and the vehicle goes straight, whereas the pedestrian is looking and stops at the curbside. We see on the top a top view of the situation with a driver gaze direction and a pedestrian head orientation marked by a line, and the predicted locations at 0.75 and 1.5 seconds marked by ellipses. Just below the top view is a graph with the predicted collision risks from the current time step up to 1.5 seconds in the future. It remains close to zero during the first scenario. In the lower part, one sees various graphs with the latent variables. In the second scenario, both driver and pedestrian are not looking at each other and are on collision course. The predicted collision risk shows a bump during the scenario. This could be used to trigger an early driver warning. At the demo day of the Intelligent Vehicles Conference in 2019, we showed how our context-based pedestrian motion prediction could be combined with the motion planner of a self-driving vehicle. The self-driving vehicle has the right of way. It approaches a pedestrian who walks laterally towards the curbside. In the first scenario, the pedestrian has not seen the vehicle and crosses. The self-driving vehicle anticipates this and performs an evasive maneuver. The pedestrian dummy feet motion is great, isn't it? This illustration shows a snapshot of the inner workings of the system. Shown are the estimated pedestrian state on the top left, the estimated pedestrian head orientation, the predicted pedestrian path, and the planned path of the own vehicle. In the second scenario, the pedestrian has seen the vehicle and stops at the curbside. The self-driving vehicle anticipates this and continues driving straight without being affected. Note that the pedestrian dummy can also turn his head, and it does so right at the beginning of the following sequence. The dynamic Bayesian network approach for motion modeling is very generic and can also be applied to other road users. Here we see its application to a cyclist that can turn left at an intersection in front of their own vehicle. Context cues in this case are at intersection, on collision course, and cyclist arm up. In the video, we see again the estimates of the latent variables as the scenario unfolds. So far, I've discussed the use of dynamic Bayesian networks for motion prediction. We have seen that its crafted representation allows it to incorporate expert knowledge, which may or may not be accurate. We can inspect the estimates of its latent variables and thus explain its inner workings. This is especially attractive in safety-critical domains like intelligent vehicles. The DBN has also the advantage to feature a comparatively low number of parameters. It can thus be applied for small training sets. One disadvantage of the DBN, however, is the higher annotation effort needed per training sample. We need to annotate ground truth in all training samples, which basic motion model is applicable, and what are the associated values of the latent variables. Another popular class of models for motion prediction involves the recurrent neural network, RNN. For better or worse, it has a learned representation. On the downside, it is not easily interpreted, and there are a lot of parameters, but it does not need any additional annotation of the basic motion models or the states of the context-related variables, such as the DBN. So then the question is, how do these classes of models compare in terms of performance? We recently performed a case study on cyclist motion prediction where we compared a DBN and an RNN at a level playing field. The scenario was the same as presented earlier, where the cyclist in front of the vehicle could turn left at an intersection or drive straight. The level playing field means A, the same context cues are explicitly provided as inputs to both, and B, not only is the RNN optimized end-to-end based on the log likelihood, but we will also optimize the DBN parameters in similar fashion. However, we will do so in a way that the DBN remains interpretable. That means that we will ensure that after optimization, the transition or dynamics matrices remain in the appropriate form. So let us look at the table of results. The first column has a DBN with some ad hoc parameter settings, as in our previous work. The second column has the DBN with the optimized parameters in end-to-end fashion. And the third column mentions the RNN. So the first and second row of the table contain the performance metrics, log likelihood, and Euclidean distance. Looking at the numbers, one sees the RNN being the best performer, but the optimized DBN closes in on the RNN performance, which could be an important finding for those applications where explainability is required. Taking a broader perspective, motion models can be distinguished in a number of classes. Dynamical systems, this is the classical approach. Future state is obtained by propagation of a set of explicit dynamics equation. We have a first-order Markov property. And here we see a trend from single motion models to use of multiple specialist models, either as a mixture or with switching dynamics, which could be guided by context features. In a second class of models, we have nonlinear regression. There are no explicit dynamics equations, but one regresses from the past and current observations to a future state. A number of recurrent neural networks, especially GRUs and LSTMs, are currently popular for this purpose. Finally, there are trajectory learning methods where trajectories are clustered and the mean trajectory representations are matched with partial trajectories obtained in online fashion. And the last class involves goal-directed planning, and these methods model road users as agents that perform a sequence of actions in order to accomplish some long-term goal for which they receive rewards. We have already seen some useful motion cues for prediction. This slide provides an overview of all cues that might be relevant. One can first distinguish the cues that relate to the target itself. Kinematics, position and velocity are certainly the primary cues. Then there is pose, head, gaze, say something about awareness and thus are indicative of the motion soon to happen. Body orientation is indicative of the current motion, and complete articulated body pose will provide more detailed info and will also capture gestures as explicit forms of communication. Then there are object attributes like age, gender, clothing. They will likely influence motion model parameterization. There has been little work in this area that quantifies their effect. And it remains debatable whether it is ethical to use personal attributes in the first place. Apart from target-related cues, there are those that relate to the environment, to the static environment, which could be just spatial information regarding obstacles ahead, or it could be road layout information, or it could be semantic information like traffic lights or zebra, which determine the right of way and strongly influence the future likely motion. The target might also be influenced by other road users, especially by the own vehicle, but it might also be influenced by other road users like cars in the other lanes. Pedestrians when crossing might also be influenced by other pedestrians that already have started crossing in a herd behavior. There is a rapidly expanding literature in the broader domain of human motion prediction. With some colleagues at Bosch and with Chris Kitani at CMU, we recently wrote a survey where we covered over 170 papers. This survey introduces a new, more detailed taxonomy of human motion prediction methods. It offers a cross-disciplinary review of the various approaches, data sets, and benchmarking metrics covering mobile robotics, video surveillance, and autonomous driving. I believe it offers some nice insights from people that have been working in this domain for some time. And as such, it is a great starting point for everyone new in this attractive domain, or for others that need a refresher. Let me summarize. Anticipating road user motion is a key remaining challenge for intelligent vehicles. I presented our work on pedestrian and cyclist motion prediction. The overall trend is to use more context cues for motion modeling, enabled by advances in perception and mapping. First datasets and benchmarks in road user motion prediction have appeared, but we need more truly large datasets containing 3D sensor data and vehicle ecomotion data. The jury is still out on what type of representations to use, handcrafted or learned. This also holds for which class of models to employ. It does look as if representations that are learned end-to-end perform better. On the other hand, as we have seen, handcrafted representations can also be optimized in end-to-end fashion, and in doing so, they can close some of the performance gap. They remain a viable option for a domain where explainability and stability are important. Another open issue is which motion cues to use, how much improvement one obtains by adding more context. Apart from performance, there might be ethical issues involved when introducing person-related attributes. Last but not least, how to scale up to big data. As you see, there are a lot of challenges left in this attractive research domain, and I wish to conclude with a quote attributed to Niels Bohr. Prediction is very difficult, especially about the future. Thank you very much for your attention, and thanks to my former and current PhD students and colleagues that did the actual work that I presented.